In this video, I'll be talking about the application of center field uh, approximation to many electron atoms. And we understand from the basics that it's theoretically impossible to exactly deal uh, with with atoms having more than one electrons, where it is practically impossible to exactly solve the Schrodinger's wave equation. So what we look for is that we look for some approximations and try to boil down the problems of these many electron atoms uh, to actually to uh, hydrogenic problem solving techniques. And what am I trying to say here is that when we have many electron atoms, we can write down the Hamiltonian for many electron atoms. Writing down the Hamiltonian for many electron atoms is not a big deal. But what's problematic here is if I talk about the Hamiltonian, if I take a Hamiltonian of many electron atoms, what we will carry here in the Hamiltonian is the kinetic energy part, which is minus h cross squared by 2m del I square. I runs from 1 to n. Then we will have the electrostatic interaction between the electrons and the nucleus. So we will have another term. We will have the term like z e square by, say, r I or j, and j runs from 1 to n. And then there will be an additional term where we will have the problem in calculating and solving, and that term will be the interaction between the electrons. And what we have here is that we have entanglement of the wave function, and uh, if I write down this sigma for the interaction between the electrons, I can think of writing e square by ri rij. So here I will run from 1 to n, and j will not be equal to I, so j will also run to n. So this j will be basically I plus 1 in every situation. Now the point is that this is the Hamiltonian for many electron atoms. And this is the kinetic energy part. Then we have the potential energy between individual electrons and the nucleus, and then finally you have this extremely complicated term and this term is to be exploited, and this term is basically the interaction between the electrons. And electrons have motions, and there is entanglement. So the point is that when we talk about the many electron atoms, we certainly have to subject these kinds of problems to some kinds of approximations, and the very well-known approximations that are used for many electron atoms. Center field approximation is one among them. Then there are other approximations like Hartree-Fock approximation to deal with such kind of systems where we have to have the problems involving more than one electrons. So now, what we do here is that we have to come up with a newly formulated Hamiltonian, and not only the Hamiltonian, we have to formulate the Schrodinger's wave equation, and this Schrodinger's wave equation has to would certainly take care of spatial part here, spatial part. And in this context, in the context of this central field approximation approach, so if I start with writing the Schrodinger's wave equation here, I choose a Hamiltonian operator, but this Hamiltonian operator has to be within the domain of central field approximation, and then we have psi c, and then we have a number of states, R1, R2, R3, and so on and so forth to Rn. And this kind of thing we can write down in terms of summations. If I take the summation for I runs from 1 to n, then minus h cross square by 2m del Ri square plus V of R. Okay, the wave function psi c, then R1 R2 dash dash to Rn, and this is equal to the eigenvalues that we will obtain for this central field approximation, and psi c will be back as R1 R2 and so on, so for Rn vector. So this is my Schrodinger's wave equation in central field approximation. Now, what is so important about this equation is that this equation represents n electron atoms, in which each electron, I mean electron I, each electron I revolves around the nucleus, independent of the remaining n minus 1 electrons. So so we have an electron in the ith state, and this electron is revolving around the nucleus, and the remaining n minus 1 electrons, what they do is they become the part of effective central potential that is created by the attractive Coulomb potential due to the nucleus, if this is the nucleus, and there is some attractive or all averaged potential between the nucleus and the n minus 1 electrons. And these the n minus 1 electrons, the charge, their potential is averaged out in the spherically symmetric central part. So the potential created due to its repulsive interaction with the remaining electrons, that is n minus 1. So what is important here is that due to this approximation, which we are talking about here, is that the entanglement of individual electron waves. There are electron waves, and these electron waves, these electron wave functions, due to their mutual interaction between the electrons, will vanish, and this we can express in some central field wave function. And what will be that central field wave function? I can think of psi R1, R2, and so on to Rn as the product of the individual electrons. I mean, individual electron orbitals, all of which are normalized to unity. So we can think of writing down the wave function psi c R1 R2 dash dash Rn as the product of the independent product of the wave function, say zeta ai R1, then zeta, let me call it A1, then AI, RI, and then zeta, AN, RN. So this will go on from A1 to AN. And what is this zeta AI? R of I. This zeta AI, it's basically the representation of the spatial part of the individual electron orbitals of ith electrons. With this AI is basically the indicator of the set of quantum numbers. Like we have Ni, Li, and Mli for each individual wave function, and it's located at a distance of Ri from the nucleus. Now, so what we can do here is that we can write down the Schrodinger's wave equation. So we can write down sigma I runs from 1 to n, then we have minus h cross square by 2m del Ri square plus V of Ri times, so instead of the wave function, we can write down zeta A1 R1 and zeta AI Ri, and so on and so forth to zeta AN Rn. And this will be equal to the energy eigenvalues En L, zeta A1R1, and so on and so forth. So the point here is that this is the Schrödinger's wave equation, which we are writing down in terms of the individual independent coordinates, independent wave functions. So the spatial coordinates that we have here as Ri, these spatial coordinates are independent of each other now. They don't depend at all with each other. So we can think of applying the variable separable technique and resolve and solve the given Schrödinger's equation into n number of, we'll have n number of Schrödinger's equations, and certainly each equation will be a representative of the motion of an individual electron in an effective central potential. In an effective central potential that's observed by that very particular electron that we have been talking about. Now, proceeding from here, what we can say is I would like to write down this for ith electron. If I write down this individual Schrödinger wave equation, I can think of writing minus h cross square by 2m del Ri square plus v of Ri, and then I'll bracket it out, and then zeta Ai, then Ri is E, and then Ai, then zeta Ai Ri. And here this Ai represents the set of quantum numbers. And set of quantum numbers Ni, Li, and Mi. So this is what defines the energy state of the ith electron. Hence, we can rewrite this Schrödinger's equation in more general form. We can write down it in more simplistic form as minus h cross square by 2m del R square plus v of R, and zeta NLML R is equal to ENLML, then zeta NLML of R. Fine. So here, what we have tried to do is that, for the sake of some kind of simplicity, we have dropped the electron indices here. We have dropped those indices to make it general Schrödinger's equation of any individual electron under this central field approximation. Okay, so proceeding from here, what we can think about is what we have here is we have